right, hello. Thank you everybody for showing up. This is our sounds like you're having. So tonight is the night of Ice and Fire, or ISS and Fire. I think first we should get a big up round of applause for coming up. About 5 minutes. All right, we're okay. Okay, so for those of you that haven't come here before, the format is that we're going to, we have 2 talks tonight. One is going to be about ISS-CREAM, which is a new cosmic ray detector that went up on the International Space Station, and then Cassini, which is a spacecraft that had been monitoring Saturn for over a decade and just recently intentionally crashed and ended its final run. So I'll have 2 talks on that. We'll have a talk first by Dr. Stéphane Coutu, who tells about ISS-CREAM. Then we'll have some trivia. Then we'll have a break, come back, get the answers. Then we'll have our last talk. I would encourage you to fill out the donation boxes, which are up front here. If you want better prizes, if you put money in there, we can get good prizes. You can vote today on whether or not you prefer the Snowball Nebula or the Fire Nebula. It's ice and fire. It's the theme here. Flame Nebula, sorry, close enough. Last time we had Captain Kirk versus Captain Picard, and Picard won by a pretty long shot, which I think is appropriate. So I think that's all that I wanted to say before we get off to our first talk. So here is Dr. Stéphane Coutu, and he'll tell us about ISS-CREAM.
Thank you. Okay, thank you very much. I'm really delighted to be here. I think this Astronomy on Tap series is a wonderful event. I don't know if all of you are professional astronomers, graduate students, postdoc in astronomy, or general folks interested in astronomy, so all of that is good. I don't assume anything here. I have a few slightly more technical slides, but we can go quickly on those if necessary. My name is Stéphane Coutu. It's a French-Canadian name, and the U sound in my last name doesn't exist in English, so don't bother with Dr. Coutu or Professor or anything. Just call me Stéphane, and everything is good. And I'm going to tell you about a funny way of doing astrophysics. In this Astronomy on Tap series, you're used to looking at the sky using photons as your messengers. That come to us in a straight line. Therefore, you can do astronomy, you can make beautiful images of the night sky, you can look at planets, stars, and galaxies. But here I'm going to tell you about learning about the universe through the study of high-energy particles that come to us from the depths of space. And what's interesting about those things is they don't come to us in a straight line. They are charged particles, they carry an electric charge, which means that in trying to get to us from wherever they came from, they are deflected by magnetic fields in the same way that the Earth has a magnetic field around us. Compasses point north because of that. The galaxy, the intergalactic separations between large bodies of masses known as galaxies, they're all permeated by magnetic fields. That means that studying the universe with particles is challenging. You can't do beautiful images of distant sources that way. But you can still learn a lot. I'll tell you about some of these efforts where we fly instruments to the top of the atmosphere with high altitude balloons or spacecraft. And in particular, I'll tell you about one experiment called CREAM, Cosmic Ray Energetics and Mass, that we flew in balloons in a series of balloon flights in Antarctica. I'll tell you a little bit about that. And most recently, a month ago, we launched a version of that on a rocket to the space station. So now there's a version of CREAM on the ISS. It's ISS-CREAM, it's ISS-CREAM, okay? Now, when we first started working on this and went to Antarctica for the first time, I came up with this logo for our mission, where there's the ISS-CREAM instrument, and this is artwork from an old rock and roll album by a band called CREAM. And to my dismay, none of my graduate students recognized the artwork. They had heard vaguely of Eric Clapton, but Jack Bruce, Ginger Baker, these were not names they were familiar with. The classics are lost on the young generations, I'm sad to say. It's a really good album, Disraeli Gears. So if you don't know it, look it up, okay? All right, now I'm supposed to talk for 20 minutes, followed by 10 minutes of questions. let's nix that plan, and instead let's make this interactive. So if you have a question, don't wait till the end. Stop me as I go. It's much more interesting if we make it interactive. I'd rather skip some slides, and meanwhile, have the conversation and stop, on the points that you're interested in so that we can make it more fun for everyone. Astronomy is an old science. People have been looking at the night sky for thousands of years. And it's only been since about 1912, so a little over 100 years, that we know that in addition to photons, particles of light coming to us from the distant reaches of the universe, there are also charged particles. And this is a discovery credited to Victor S., an Austrian physicist, who conducted a series of balloon flights above the Austrian countryside. And he would take his elementary particle detectors, these were primitive detectors, up to 17,500 feet. And he was looking to study a strange phenomenon that had been reported, that there was a strange kind of radiation that was present in the atmosphere. And everyone thought it came from the ground. And if you went up in a balloon and detected that radiation, it should decrease with altitude. That's what Victor Hess set out to prove. Instead, to his surprise, he found that as he went up to higher altitude, there was more of that radiation present. It didn't seem to come from the ground. Instead, it came from above the atmosphere. So what caused this was very confusing for a while, but it was ultimately identified as what is now known as a cosmic ray. In other words, it came from outer space. So that source of ionizing high-energy particles in the atmosphere was something that came from above. That was 1912. 100 years later, we're still trying to find where they come from. Okay? And there's a lot of challenges associated with that, and you'll see why it took 100 years to get where we are today. The prevailing thinking nowadays is that cosmic rays can be made in the remnants of supernova shock waves. Here's a picture of what is called the Crab Nebula. It was first seen as a new star in the sky in 1054. It was reported as a new light that appeared in this night sky. And to this day, 1,000 years later, this is the Crab Nebula seen by the Chandra satellite X-ray experiment and the Hubble Space Telescope in visible frequencies. And what I'm going to try and show you is a series of photos taken months apart of this object today, 1,000 years later, where you see the streaming motion, these shock waves that are still present in the environment of the remnant of that supernova 1,000 years later. So these gigantic explosions that take place in our galaxy, we don't know how often this happens, maybe every 100 years, maybe every 200 years, somewhere in the Milky Way galaxy a supernova goes off. But once it does, this shock wave seems to be something that happens for the better part of 1,000 years. And there is a model that associated with this kind of streaming motion of these shock waves, you could have particles, charged particles, atomic nuclei, get swept up and accelerated, and then become part of what are the cosmic rays flying through the galaxy. But we'd like to see, how they get to Earth, since we're studying them at Earth. The problem with that is that they don't come to us in a straight line. These cosmic rays are charged particles, so they're constantly deflected by magnetic fields over the millions of years that it takes them to go from their source to Earth. So it's a challenge, and there's a lot of physics going on along the way. Those particles, even if you understand how they're made, have to get to us. So they are deflected, they interact with the stuff between the stars. They might escape the galaxy if the magnetic fields are not strong enough to keep them inside. So there's a lot of physics there. Then they get to near the Earth, and they run into the environment of the sun. Well, the sun has this outgoing flow of particles called the solar wind. Those particles come to us from outside the galaxy. So they have to swim upstream against that river of particles flowing away from the sun. So that modulates their ability to get to us. Then they get to near the Earth, and the Earth has a magnetic field that deflects them, that influences their detectability, and they might interact in the atmosphere. So there's a lot of physics in going from what you see at Earth to trying to understand how nature made these particles in the first place. There are models going back to 1942 or so by a very smart guy named Enrico Fermi, who said such shock waves in the universe might serve to make high-energy particles, accelerate them to gain energy up to an energy, this is a high-energy physics unit of energy, but up to an energy of about 10 to the 15 electron volts. So the theory works up to a point. Beyond that energy, we still see particles that are even more energetic, but it becomes a real challenge to see how nature does this. So let's try to keep that number in mind. So once you start studying these particles and you detect them and you do 100 years worth of experiment, what do? Well, the simplest thing is you just count them. You count how many cosmic rays you detect as a function of how much energy they have. But this is a plot on logarithmic scales, so it hides a lot of sins. And one of the sins it hides is that this range of energy values covers 11 orders of magnitude in energy. Okay, that's the range in going from 1 cent to $1 billion. Okay, so the 1 cent particle, there's a lot of them. The $1 billion particles are very rare. And how rare does that become? Well, in the time that it takes, to go from 1 cent to $1 billion, the fluxes of particles drop by 31 orders of magnitude. Okay, there's no more a good image that you could carry in your head to convey that kind of range of values. It's just too big. So this is a huge drop. Now, it doesn't look so bad on this scale because I use logarithmic scales. Moreover, I use a trick here of multiplying the y-axis value by e squared. So that has the effect of taking something that really falls like a brick with energy and rescaling it so that you can start seeing some of the details. So it really falls a lot faster with energy than the graph would lead you to think. And this is a compilation of experiments done using mostly arrays of detector on the ground, air shower arrays. And if you look at this distribution, you see that for many decades in energy, there's a straight line dependence here. On a logarithmic scale, a straight line is a power law. It's e to the power minus 2.65. And all of a sudden, there's a different straight line. There's a steepening to e to the minus 3. We would have to understand this, how nature does this in the acceleration regions. And at the very highest energies, maybe there's also a different change of spectral index to e to the minus 2.6. So this general shape has led people to describe the spectrum as a bent leg. This is Michelangelo's David. And this feature is called the knee in the cosmic ray spectrum, and this feature is called the ankle. What do we think is the interpretation of these changes in spectral indices and the value of the slope? We think that the knee is the energy at which this idea of the shock acceleration in supernovas running out of steam, that the energy gain in these accelerators in the cosmos starts to die out at right around 10 to the 15 eV. And that's what Enrico Fermi had told us. So that seems to agree with that idea, that the shock waves have something to do with it. And then at the highest energy, the ankle is probably a transition where all over the spectrum we're looking at particles from our own Milky Way galaxy. At the highest energies, we're starting to see particles from outside the galaxy that are from even more extreme astrophysical environments. Why has it been taking 100 years to get this picture? At these kinds of energies, if you were able to build a detector and put it in space, and it's 1 kilometer by 1 kilometer, a solid square kilometer detector, and you wanted to catch those particles in the act, it would take you 100 years to see one particle. That's how rare they are with that enormous detector that you couldn't build anyway. So the net outcome is that techniques to study these things are limited to, if you build an instrument and send it to the top of the atmosphere with a balloon or a satellite, you can reach about almost to the energy of the knee. And that's what I'll tell you about. That's some of the experiments we're doing. And at higher energies, you have to resort to letting the particle hopelessly not hit your detector because they're too rare. You hit the atmosphere, you make a big splash in the atmosphere, and you measure the particles that reach the ground. You use the atmosphere as part of your detector. So these are indirect techniques. We're involved in that too, but I'm not going to tell you about that today. But from the direct measurements, if we catch these particles and we see what they are individually using techniques of high energy physics, you can see that 85% of the cosmic rays are protons. Well, a proton is the nucleus of a hydrogen atom, and hydrogen is the most abundant element in the universe. So it's not too surprising that nature is able to take the most abundant particles, somehow rip out the electrons, have a naked nucleus, a naked proton, and accelerate it, and it makes the bulk of the cosmic rays. The next most abundant element is helium. Helium is the second most abundant element in the universe. It's also the second most abundant element in the cosmic rays. But there's a fascinating contribution of more massive nuclei, also electrons. There's high energy particles that are electrons instead of nuclei. There are antimatter particles. That's a whole separate talk that are part of the things that hit the atmosphere. There are isotopes of different types of nuclei, ultra heavy nuclei. All these things are interesting. So in detecting these particles, we really use the tools of high energy physics. Our telescopes don't look like astronomical telescopes. They don't have mirrors and cameras and collecting the light from mirrors. Instead, we watch the cosmic particle come through and deposit energy in different types of particle detectors. If you went to CERN, to the Large Hadron Collider, and went in one of their cavities and looked at the big particle detectors that they have, they would look like this, but much bigger and much more expensive. So we have scintillation detector, transition radiation detectors, Cherenkov plastic detectors, silicon charge detectors, a set of targets to make the particle create a shower, a calorimeter to detect the shower. Never mind what all these things do. Taken together, we use the signals in these instruments to measure the charge of the particles, what type of nucleus it might be. These nuclei are all fully ionized, there's no electrons, and also how much energy every one of these nuclei has. So that's how we determine what they are and how much energy they have. So if you have a simulation on top of the schematic of the instrument of a very high energy nucleus, maybe an iron nucleus, coming through, it lights up a bunch of our detectors. It interacts in the carbon target, makes a big splash at the bottom. And from all the electronic signals that we read, we send everything back down to the ground. We reconstruct the properties. And meanwhile, a picture of this instrument is shown here with a Penn State graduate student at the time who was working on the project. So it's a complex, dense array of particle detectors with low power electronics to read out everything. And then you take this to Antarctica and fly it on a balloon and collect as many particles as you can. Now, I'm told I'm supposed to tell you anecdotes and stories, and this is very dangerous sensors, and we have a total power budget of 400 watts through these solar panels. It's not that much. So all of our electronics is custom designed, low power electronics, built in my lab by my students. You have to test everything, make sure it's going to work. And the solar panels are nice because when you go to Antarctica, you go down there in November, December, it's the local summer. And as you fly around the entire southern continent of Antarctica, you keep the instrument pointed at the sun throughout the flight. The sun is up 24 hours a day, so you have constant power. You don't have to lift a lot of heavy batteries. Now, Antarctica is an interesting place. So the first thing you do is you fly to Christchurch, New Zealand, where there's an Antarctic Operations Center, where they outfit all the participants to various Antarctic campaigns with equipment to deal with extreme cold weather situations. I'm a native of Canada, it's a French-Canadian name, so I'm used to dealing with winters, cold winters, and yet this was a ridiculous amount of clothing they outfitted me with. I had 11 different kinds of pairs of mittens, gloves, gauntlets, liner gloves, to deal with any possible contingencies in case of extreme cold weather in Antarctica. Once they outfit you with this, then they put you on a military transport plane. This is a C-17 cargo plane, and they fly you from Christchurch to McMurdo Station in about 5 hours. This is a cargo plane, so you're sitting in the back with cargo equipment strapped down to the floor. The cabin is not soundproof, so everyone is wearing earplugs. It's very loud inside. There are no windows, so you don't get to see a lot of beautiful landscapes going south. But then you land on the ice, and this is McMurdo Station in Antarctica. So it's a very utilitarian-looking kind of base with dorm facilities here, a variety of labs, things like cafeterias. It accommodates about 1,000 people during the summer season, which is where the ice can melt and you see the dirt of the station come through the ice. And here in the foreground is an old wooden hut built by Robert Falcon Scott and his men in their last Antarctic expedition. That was their attempt to go to the South Pole. That building has been there for over 100 years and it still stands today. So it's a fascinating place with a lot of history. If you go to McMurdo and you turn away from the station, this is Ross Island. McMurdo is at the tip of a peninsula at the southern end of Ross Island. And in the distance you see Mount Erebus, Mount Terror. These two mountains are dominating the landscape, and Mount Erebus is a volcano. It's not active, but it's always got a little bit of steam coming out the top. So it's the southernmost active volcano in the world. This is this hut built by Robert Falcon Scott. And even though it's been there for 100 years, it was built well, and the wood never rots down there, so it's still there today. Right outside the hut is a carcass of a seal that was killed by Robert Falcon Scott and his men. They were intending to eat it, but this was late in their last season of being there, so they decided to leave and they left it out there. So it's been out there since 1913, and it hasn't completely disintegrated away because it's kind of mummified now. It's dried up. Antarctica is very dry. There are no microorganisms that could come and eat it up. So you can still see the flippers. If you went to look at its face, you'd see whiskers and teeth, and it's remarkable that it's still there. You can borrow a key and go to visit inside the hut. It's now a World Heritage Site, and you see equipment left behind 100 years ago by these last explorers to have been there. And there was corporate sponsorship taking place as well. A lot of the equipment crates were stamped with, in this case, Home Light Lamp Oil Company would stamp the crates for Scott's Antarctic expedition of 1910 to 1913. So in sponsoring the expedition, those companies would do things like that. If you're there long enough, chances are you might see some wildlife too. So as a little bit of a detour, here's a picture I took of a mother skua and her baby chick. Skuas are a kind of dirty Antarctic scavenger seagull. Here is a minke whale that came to feed off the rich Antarctic oceans just about a quarter of a mile off the coast in the distance. You would hear it blow its water spout, and then you could spot the water going off. Here's a picture of a Weddell seal sunning itself on the ice. The rules of the Antarctic Treaty are that you can approach wildlife to the point where it reacts to you, at which point you're too close and you should leave it alone. Weddell seals, after they're digesting their krills and shrimp and whatnot, don't react to much of anything, so you can take these amazing pictures. Here was a bunch of emperor penguins for a while that were sunning themselves on the ice, molting for several weeks, changing their plumage. And then here's a bunch of Adelie penguins that we found once, 44 of them, that were feeding in the water. And after they came out of the water, we were sitting there quietly. They walked right up to us. So it wasn't us approaching them, it was them approaching us. They were about 3 feet from us and completely unafraid, just curious. They don't have any predators down there. At one point, they decided we weren't all that interesting and they scampered off. The reason we were there, though, was to launch one of these instruments. So here's my video footage of one of our balloon launches. And this is an enormous helium balloon filled with helium gas only at the very tip of the balloon. And as NASA is letting this go, you see these big semis were filled with compressed cylinders of helium gas. You see that the balloon is mostly uninflated. And as the whole thing will start going up through the atmosphere, the decreasing atmospheric pressure with altitude will cause the gas to expand, and eventually the balloon will fill up. When the whole thing is vertical to the ground, if necessary, if there are any residual wind speeds, The crane might drive a little bit to match such wind speeds to give the instrument a very gentle launch. And you'll see in a second they'll let it go, and the instrument hardly suffers any shaking or jolting at all. It's a very gentle way to launch an instrument to the edge of space. It can rise up to about 130,000 feet, which is well above any altitudes where aircraft can fly. And in case you're interested, you can pass this around. This is an actual piece of one of our Antarctic balloons, and you'll see it's a little thicker but similar in consistency to a dry cleaner bag. But one balloon has 12 acres of this. This is how big these balloons are. When fully inflated, they're 40 million cubic feet of volume. And at the end of the flight, when the instrument has flown maybe a couple times around Antarctica, it's time to terminate the flight and get the instrument to land on the ice. Where's my video at? This is the one. And here's video footage of a camera looking up at the balloon at the end of the flight. You see that the balloon is fully inflated. The instrument is looking up, so now the instrument is falling through the atmosphere. The balloon rips open and a parachute automatically deploys. This is daylight because you see the sun is right off the edge of the screen, but the sky looks black. That's how you know you're in space. It's not blue. You're high enough that you're above the ozone layer. And now the instrument is coming down, and it takes almost half an hour to go from these very high altitudes to land on the ice. So that's the logistics of a balloon flight in Antarctica. Now, if everything goes well and the instrument lands undamaged, then you go out to recover it. I lost my cursor. There we go. And here's one of our instruments that had landed, stayed upright. We flew out to it with a twin otter plane on skis. We worked for 3 days out in the field to dismantle it and bring it back to base. So these flights going to Antarctica gives us very long exposures. When we launched from McMurdo Station, one of our flights here circumnavigated Antarctica 3 times. 1, 2, 3. It stayed up, in this case, for 38 days. And the circumnavigation pattern at these very high altitudes are great big circles centered on the South Pole. So by launching from McMurdo, we return close to McMurdo, which makes it easy to recover, quote unquote. It doesn't land very far. So we've done this now 7 times with different flights where we've accumulated 187 days worth of data. We have the world's largest statistics of measurements of cosmic rays of any instrument because of these repeated Antarctic missions. And I don't want to dwell too much on some of the technical aspects, but here, for example, is a distribution of different types of cosmic ray nuclei we measured in flight. This is at energies unprecedented, where no other instruments have been able to see those nuclei. And you see we have hydrogen nuclei, helium nuclei, beryllium, boron, carbon, nitrogen, oxygen, all the elements of the periodic table. And now we do things like measure their relative proportions. Hydrogen and helium are very abundant. They're the most abundant cosmic. Yes, please.
I was going to ask, what's the limiting factor on how long the balloons can fly for?
Yeah, so why couldn't we fly longer than this? In fact, the record so far is 54 days. And it's only limited by how late you go in the season. And are you willing to let it go longer? If you do, you won't recover it that season. You might not recover it at all. Because eventually it's possible for some of these trajectories to start spiraling out, and the instrument ends up flying over the Antarctic Ocean, and there you will not recover it. It will land in the sea. So if you want to get it back, you're limited in up to about 54 days is the longest that's been done so far. But there's nothing intrinsic to the gas in the balloon and the escape of helium from the gas that limits the flight so far. It's been other considerations. So in principle, you could go perhaps as long as 60 days or something like that, which is remarkable.
Wait, do they remain tethered to that vehicle then?
No. So the balloon is flying off, and then you just track it using GPS systems and telemetry through a NASA satellite system called TDRS. You know where it is, you can communicate with it, you can control voltages, there's a computer on board, and when it lands, you want to land it, you can send a command to separate the balloon from the parachute. It's all done with no There's a certain amount of autonomy built into the computer system that drives the instrument, and the rest is ground control from people monitoring this 24/7 when it's in flight. So it's an interesting way to get at your science. We look at certain mass peaks in the data to help detect those more abundant elements. And one of the nuclei of interest is boron compared to carbon. Studying the boron to carbon abundances has been able to give us a handle on the history of cosmic rays propagating through the galaxy. For the experts in the audience, the carbon nuclei come from the supernova sites directly. The boron nuclei are made in spallation reactions, nuclear reactions of cosmic rays through the millions of years of transport through the galaxy. And in terms of a distribution of some of our measurements of boron to carbon, compared to model predictions, these various curves, we're able to zoom in on which model agrees best with our data. That helps us define the parameters of the cosmic ray propagation through the galaxy. So this gets a little more technical. Let me quickly skip through a bunch of this stuff here. We're measuring the energy distribution of these cosmic rays, mapping out their slope and details. No one has been able to do this to this level of accuracy. So it's been a very fruitful series of measurements. But with 7 flights in Antarctica, we still have 180 some days or 166 days of total exposure. The cosmic rays get more rare with higher energies. We'd like to do better. And this led us to develop a version of the CREAM instrument intended to launch to the space station. This is this ISS-CREAM idea. So it's, again, a particle physics experiment with silicon detectors, carbon targets, scintillators for doing top and bottom charge detection, a calorimeter, and at Penn State we built this device down here called a boronated scintillator detector. We built this, tested it. We had to do things that you don't need to do with a balloon instrument. For example, you have to put the instrument on a shake table, make sure that it will survive the rocket shaking at launch. And we had to satisfy a number of NASA requirements. And just a month ago, this was me at the Kennedy Space Flight Center with the SpaceX 12 rocket. This NASA that no longer flies rockets. They have companies do it for them. SpaceX is this Elon Musk company. That's remarkable. This was the launch of the rocket. It was a beautiful day, very successful launch. Once the rocket got up to orbit, when the rocket separated from this capsule, you see our instrument is there, stored in the cargo part of the capsule. Eventually, solar panels deployed, and after about 2 days of orbital maneuvering, the capsule reached the space station, and our instrument could be deployed. And just to show you quickly, I have this 1-minute launch video given to us by SpaceX of the initial rocket launch coming off the launch tower. This is the same place that the Apollo 11 mission to the moon took off from. So it's a historical place. The rocket is separating now the first stage from the rest of the second stage plus instrument, and the main rocket turns around and comes back, which is a new thing SpaceX does that's really kind of surreal looking. You'll see the landing of the primary rocket in a second. The secondary rocket now pushes the instrument up into space, and now the first stage of the rocket comes back and lands on the ground. It's empty now, all the fuel is gone. They're able to guide it back to the ground and get it to land, and it stays perfectly upright and it can be reused. It's really surreal looking. And here's the last separation with our instrument inside, solar panels opening up, reaching the space station. So about a week after the launch, they managed to get it up there. They managed to grab it with these manipulator arms, install our instrument on the exposed platform for science on the space station. And for the last 3 weeks, we've been turning on the detectors one after the other, adjusting voltages, setting thresholds, understanding the performance of the instrument in orbit. So we're just starting with the science program of this. I just wanted to throw a slide here of the various graduate students at Penn State who have been working on this project. They've all had to learn how to build detectors, how to test them, how to qualify them, make them work in the upper atmosphere. They all got to travel to Antarctica, participate in these balloon campaigns. They all got to help recover the instrument, do simulations, do data analysis. It's a complete training of all aspects of experimental physics that people go through. So I've gone too long. Let me throw up a bunch of conclusions. The balloons we've been flying are much cheaper than rockets. And by going to Antarctica repeatedly, we've been able to accumulate, so far, the largest world statistics of the direct cosmic measurements, cosmic ray measurements, with 7 separate Antarctic flights. But now that we have ISS-CREAM on the space station, after 1 year of operation, we'll certainly beat what we've been able to do with balloons. So it will not take much time with 1, 2, 3, maybe longer years of exposure to even beat what we were able to do with balloons. We're also involved in a new project that just got funded by NASA to fly another experiment in Antarctica. This is an experiment that's reusing the same condom, the superconducting magnet, so we'll use that again. Not sure if we'll put condoms on it this time. So we're learning a lot still 100 years after the discovery of cosmic rays. It's a mature field, not as old as astronomy, but there's still surprises, there's still mysteries. We're still trying to understand how nature does these high-energy astrophysical processes, and we're getting new experimental clues to bring to bear on all of this. Thank you very much. Yes, please.
I have 2 quick questions. First one, it seemed like you had vectors traced out for each detector. Do you bother to calculate the vectors as the particles enter the detector?
Yeah, so we track the trajectory of the particle through all the detectors. A lot of the measurements of the amount of, say, scintillation light deposited by a particle depends on how long the track was. If a particle track is vertical, it goes through a small amount of material. If it comes in at an angle, it goes through a longer track that deposits more light, and you have to account for that.
So it's not necessarily meaningful project because of all of the influence of the electromagnetic field. It's not meaningful.
You can't point back to its source. That's exactly right. So in fact, we don't bother with any sort of pointing. There are telescopes that operate at these altitudes on balloons. They need to understand their pointing, so they have things like star finders to know exactly where the instrument points. We don't do that because, for us, it would not give us information that we could do anything with.
The question quickly is, so it seems like you have eggs in one basket in that you said if you don't recover your device, you don't recover any of your data. Is that true?
Okay, so that's a good question. We try to beam down to the ground in flight our golden events. So if the instrument should get lost, we can still get science out of it, and the mission can still be called a success. Ideally, if it lands in a tough region of Antarctica, you go out there, and if you recover nothing else, you recover the hard drive. And there have been cases of instruments eventually abandoned on the ice that was too dangerous, but they got the data back. So you try to get at least that much back.
So you are beaming some sort of macro data back.
So that's right. There is a limited amount of telemetry bandwidth for communicating with the instrument in flight through this NASA satellite system. It's the same system that communicates with the space station, and priority goes to things like space station operations. A balloon in Antarctica, they give us some amount of bandwidth, but a limited amount.